Friday, and I have great assignments for you guys. This one was out of 50 points, so it says at the top how many points out of 50 you got. I know I have at least one student who hasn't turned theirs in yet. Okay. If everyone here has turned it in, then that is fine. I'm just going to lay these out here at the top of the room. Name out first. You guys can come collect them as you will. Overall, very good. So, I recommend you guys come up with those whenever you wish. Here's my answer key. Oh, sorry, there at the top. Not many things that were commonly wrong across the entire assignment. Overall, everyone did pretty good. I know there was less work to show this time, but as a general rule, be sure to show your work. At least show what you put into your calculator. Helps me know where a mistake might have been made. As you are collecting those, let me know if there's any specific questions you have. One minor thing as you're looking those over is a brief reminder about logarithms and natural logarithms. Whenever you type, whenever you just hit the log button, you put that into your calculator, just this by itself is already log base 10. No further modifications required. So when number 10 says to find a log base 10 of 6.2, you just need to hit the normal standard log button, because all normal logs, unless otherwise specified, are assumed to be base 10. If you want to check that for yourselves. Find where my calculator's hiding. There we go. If you do log of 10, it comes out to 1, because that's how many times 10 fits into 10. Similarly, if you do the natural log of e, you'll get 1, because that's how many times e fits into e. So the log base 10 is this one. And the natural log is the ln button. In general, just make sure to be very careful every time you put something into your calculator. There's probably one calculator mistake that did show up frequently, and it is an issue where, say you were trying to get the calculator to do something like in number 6, where you wanted 2 raised to the 3 times the e power, and then everything else present. When putting this first part into your calculator, we're just going to focus on this part for right now. We would do something like 2 raised to the 3e power, and we would need to subtract 8 eventually. We would probably put the first part in parentheses just to make absolutely certain that it didn't subtract the 8 first, or that to make sure that didn't interfere. But this by itself won't get us the correct answer, because the calculator is designed to do exponents first. So it would do 2 to the 3, and then it would multiply that answer. by 80. So whatever the exponent is, I like putting the whole thing in its own set of parentheses. When in doubt, more parentheses is usually not a bad thing, as tiresome as that will get. Additionally, it's also okay in future assignments to solve things in chunks, work things out one piece at a time. Some questions I would recommend that. In fact, there's some questions on homework number 3 where you have to, like all of our quadratics. I would like us to spend some time looking at a couple of key problems on homework 3 today. But before we move on to that, just to open the floor, any questions at all about anything from this second assignment? About your grade, about how something should have worked, anything along those lines? Okay. We've already talked a lot about homework 3, and the main things I want to look at are some of the last couple of problems, because number 17 and 21 both have a whole lot of algebra about them. So I would like to help you guys set those up today. And that's my main objective. We're ignoring 18, 19, and 20 are more straightforward than 17 and 21. So I definitely wanted to cover how to set up 17, which will also show you how to set up 21. And then from there, we can talk about anything else you guys have in mind. Yes?
I just want to make sure, you did say cross out number 18, right?
Correct. Cross out 18 because that requires a graphic function, which not everyone has. We're going to cut out graphic for this version of the class. Because odds are, if you end up taking Physics 1500 next semester, it's going to be with me more than likely. And the graphing doesn't usually come up. So, not a requirement. I know that isn't teaching. So, let's go ahead and together look at 17. 17 has a big funky looking equation in it, and our goal is to solve it for d. So, we are given several constants designed to plug into this particular formula. And just to talk a little bit about the physics, this formula has to do with the gravitational forces between 3 different objects. We have within this formula 3 different masses for 3 separate objects, and the distances between those objects are represented by the r's and the d. And g is the universal gravitational constant. You multiply that by the masses, and it simplifies things down into what the force between those 2 objects would be. So this particular formula, you are balancing the forces between 3 different things. And I want to go ahead and draw your attention to 21. I'm just going to write that down here really quickly. 21 has k q1 q2 over d squared equal k q2 q3 over r plus d squared. You notice any similarities? The format's the same. There's very similar things all in very similar places. And the question asks us for both of these to do the same thing. For both 17 and 21, our goal is to get d equals blank. Ultimately, to do that, we're going to need to use the quadratic. But before we even get to the quadratic, we need to get these into the forms that the quadratic formula will accept. So we need to figure out how to turn both of these into our ax squared plus bx plus c equals 0 forms. We need to turn these into this. It's possible, but it does take a lot of algebra. And I'm going to do that algebra with you. I'm actually going to recommend we don't put any numbers in yet. Because if we put the numbers in now, we're just going to have to rewrite them all 8 million times. Additionally, before putting numbers in, a few things are going to cancel out, meaning we don't have to use them again. And if we can, say, get this one into the correct form without numbers, it'll be a lot easier to translate this one directly into that form. So I'm going to work 17 with you, which will give us the formula for this without any numbers plugged in yet. And eventually that will also show you what you need to do on 17 without having, 21, without having to do the same number of other steps. You can just skip from one straight to the other. So we're gonna start with 17. Actually, before we do that, this formula is about gravity. Gravity between 3 different things. This formula looks so similar because it's about the electric forces between 3 different things. Q is the variable we're going to eventually use for things like electrical charge, like protons and electrons. And the reason the formulas look so similar is because gravity and electrical forces are cousins. They work very similarly. They're both 2 of the fundamental forces that hold the universe together. So in your other physics classes, there's going to be a lot of comparisons between the 2. This is where it begins. I'm going to erase 21 just to leave a little more room for 17, because this is going to take a lot of space. So our eventual goal is to arrive here. We want all the d's on one side. One of those is going to have a d squared, one's going to have a normal d, one's not going to have a d at all. So the thing we should be aiming for slowly is getting all of the d's together on one side of the equal sign. Right now, there's d on both sides and in the denominator on both sides, so we have some work cut out for us. But before we do anything else, what can we do to make our life a little bit simpler? Just looking at what's on both sides of this equation.
Multiply the d squared.
We can't do that, but there's something even before that that we can do to make things even easier for ourselves.
Square the r plus d.
That's going to be our next step. You're good. You guys are good. You're getting to the things we need to do. But I encourage you for every question to always look at your formula to see if anything will cancel out so that you just don't have to deal with it ever again. If something is present on, well, okay, this works specifically because there's only really one term on each side. There's one combined mess of things being multiplied, divided together here, and another complicated mess of things being multiplied and divided over here. Both sides of this have a d in them. We want to get those on the same side together. So we don't want those to cancel, really. We can move them around. But both of these fractions have a g and an m2 on the top. We can use that to our advantage. We can just get rid of them completely. So let's say our first step is multiplying both sides by 1 over gm2. We're going to do that to both sides. Because we have to do it to both sides. And in doing that, cancel g and the m2 on both sides. If it's present on both of them, it factors away and it just never really matters. Which means after doing this step, that's two whole numbers you don't ever have to actually put in your calculator. And it'll make all of our algebra moving forward a lot simpler because we literally don't need to write them ever again. So, with those out of the way, our new revised formula looks like m1 over d squared equals m3 over r plus d squared. So, I recommend that as the very first move. Now, there's fewer things to write every single time. Next thing we should do is, as suggested, we should probably FOIL this so that the d's are no longer trapped inside of a parentheses and we can start to manipulate them. So, r plus d squared is really just the same as r plus d times r plus d. So this is just a FOIL. We're going to do r into r squared, r into d, rd, d into r, rd, and d into d is going to be d squared. Which means we can write this instead of r plus d squared. It might look like more, but this was a necessary step. We have to deal with that exponent before we can get the d's inside of it out. So, next line down, m1 over d squared equals m3 over r squared plus, I'm going to compress that to 2rd, because there's two rd terms being added together. That will simplify to 2rd plus d squared. So, thoughts on next step to get to our goal?
Multiply d squared.
Okay, we can multiply both sides by d squared. I'll put that in green ink. That'll help us in our goal of getting this d squared out from under the numerator, out from the denominator on one side. Multiplying both sides by d squared, we'll cancel it on this side and put it in the numerator on the right. So I will rewrite that now. I'm going to erase this. Looks like you've already recopied it over there. So we completely cancel d2 on the left, which just leaves our left side as m1. That'll be equal to m3 times d squared over r squared plus 2rd plus d squared. Yes?
Why doesn't it cancel out on the right side again?
That is a good question. On the right side, we multiplied that side by d squared. That's in the numerator. So multiplying this fraction by this fraction, we put it in the numerator with the m3. So this is the full form before doing anything else. So the d squared we just added is in the numerator, and we still have our denominator. Now, the entire numerator is being divided by the entire denominator.
It's because it's being added, right, in the denominator?
Right. There's a bunch of terms in the denominator all together at once, and they don't all have a d in them. Excuse me. namely this one. There's no d present in this term at all, meaning there's no d there to try to cancel with what's on the top. Tragic as that may be. So legally, this is what we've got. There's no further way to simplify this by itself without performing more algebra and moving more things around. So, professional notice, this does not cancel further. Because the bottom is being added together, you should really put all of that together in parentheses. You need to rectify the whole of it before you can start dividing with the numerator. So since they're all still stuck together in the denominator like that, and they can't cancel with the top, what's our next move?
Plug in the number.
We could do that, but that wouldn't actually affect the d's at all. The d's would still be there, there'd just be a bunch more numbers instead of letters. And I'm going to recommend we hold off on adding the numbers until we get to this point, because then we're just going to have to keep writing the numbers over and over again. And a couple of these numbers are pretty big. So there are going to be times where you want to do the algebra before you plug numbers in, which is a big pain for me, because sometimes I jump straight to the numbers to try to get them to start simplifying and canceling. But this is not one of those times. So, if not numbers, you could put numbers in here, but I'm trying to save a little bit of board space. What next?
Would you multiply the whole denominator with both sides?
We can multiply both sides by the entire denominator. Because this is stuck in the denominator. We can't do much with it. We need to get it in the numerator, because that's where we want all the d's anyway. All this is stuck together as functionally one term right now, so we need to send the whole thing over, which would look like this. Gesundheit. So we're multiplying both sides completely by the inverse of the reciprocal. Multiplying both sides entirely by r squared plus 2rd plus d squared. That will cancel with this denominator and effectively just send it to the other side. It's worth noting, though, that we have now multiplied the entire thing by m1. We're not adding m1, we are multiplying it by every single term present. So to write the next line, open parentheses, r squared plus 2rd plus d squared, close parentheses, all together times m1 equals m3 times d squared. We're closer than we've ever been now. All the d's are in the numerator finally. But they're still spread across two separate sides. So we need to start working towards moving them together. Thoughts on next step?
Try to get that last d squared to the other side.
Yes, we do need to do that. This d squared is being multiplied by the m3. So what do you think is our best bet for getting it over right now?
I guess you could divide it. There's d squared on the other side.
Correct. However, if we were to, say, divide the d squared over to this side, we would end up in virtually the same position as right here. Now a d squared would be in the bottom, and it doesn't cancel with what's on the top because not every term on the top has a d in it. So that particular step won't work here. We want all the d's together on one side, but dividing this d over isn't going to help. Now, keeping in mind what we're trying to shoot towards here, all the d's on one side and a 0 on the other,
Could you
I'd
subtract
say,
it, the entire term?
yeah, we can just subtract the entire term over. I think that's the best move for getting this to the other side eventually. We can go ahead and do that. We're going to subtract both sides by m3 times d squared. We're just going to move the whole term over. That, I suppose I should specify what order over to come. I recommend doing this vertically on the page, kind of hard on a wall like this. That's going to give us, open parentheses, r squared plus 2rd plus d squared, close parentheses, all of that times m1 minus m3 d squared equals 0. Since we multiplied this whole thing by m1, it's still trapped inside of this parentheses, because it's the whole thing is being multiplied by m1, meaning that it's still a separate term. This is all still one combined separate term from what we just subtracted over. Which means we are not yet free to start combining d squared terms. So what's our next step?
Distribute out the m1.
Very good. We can distribute the m1 into these parentheses. That's going to give us r squared m1 plus 2r m1 times d plus m1 d squared. And that's every single term with the m1 distributed in. So we get rid of our parentheses, these are now free. But then minus m3 d squared equals 0. We are now so very close to our quadratic form. We're almost there. All we need to do is rearrange a few things and combine a few things. To get this properly resembling what we want in order to put it into the quadratic formula, we're going to need one term with the d squared attached. And we're going to want to put that one out first. There's presently two terms in here with a d squared. M1 d squared minus m3 d squared. What would a combined term resemble?
With the d squared distributed out.
Yes. I'm going to, first I'm going to write things in the correct order, and then I'll do the distributing out. Our A term is the one with the two d squareds. Sorry, with the d squared. So I'm going to put both of those at the front before I do anything else. We're going to have m1 d squared minus m3 d squared. Then in our form, the second term we want is the one with a single d on it, not a d squared. There's only one term present with only one d. So that's going to be 2r and 1d. And then lastly comes the term with no d at all, r squared times m1. And all of that is equal to 0. You're so almost there. We need to compress these into a single term. Both of these have the d squared attached, meaning we can distribute that d squared out, which I recommend you put this as a second line, but I'm just going to show the transformation, save a little board space. Those can combine to open parentheses, m1 minus m3, close parentheses, times d squared. Does anyone not understand that logic? Okay. So this is admittedly pretty funky looking in all disclosure. But, zoom tight, it's in the form we want. Our goal is to eventually get t equals blank. We have our d squared, our d, and our not d, so we can put this into the quadratic once we establish formally what a, b, and c are. A is always what's being multiplied by the squared term, which means that m1 minus m3 is our A. B is whatever's being multiplied by the single d term. So our B term is 2rm1. And lastly, our C term is whatever doesn't have a d attached. So that is r squared times m1. What one could now do is, you know what M1 is, what M3 is, what R is, and you can figure out what your A, B, and C are. You can use the numbers, use the math to get A equals blank, B equals blank, C equals blank. Then we can pop them into our quadratic. How you guys doing? Okay, I had some nodding, but I'm also getting some what is tricky? What is problematic? I want to know. Yes.
So you can't just like, when I did, I wrote down all the numbers and I didn't even get to plug it into anything. I was just trying to fill in numbers.
Okay.
And then if you get to here, you said you had to solve for each piece and then plug them into the quadratic?
Yes, since we are in this ABC form, the way to get our two answers for D is to use the quadratic equation.
I was thinking, but there's no numbers other than 2, so I have no idea where to get with that. Like you plug in those values?
Yes, the problem says at the very beginning, if G equals blank, R equals blank, M1, M2, and M3 equal blank, then, using the original formula, tell us what D is. So we have numbers for all of these constants. Now we just need to start using them. And I'll do that with you guys. I wanted us to get here because in this form, we can very easily rewrite this to fit 21 as well. Because in 21, the starting formula looks exactly the same. It's just got different letters and places. Which means by just swapping what those letters are, this is true for 21 as well. We can show what that looks like in a minute. For right now, we'll get A, B, and C written out as numbers. How about that? Where's my eraser? So, we've established that A is going to be equal to M, why is my M like that? M1 minus M3. So, M1 is defined as 324, and M2, sorry, M3 is defined as 1.03 times 10 to the 24th, positive 24th power. The reason that these numbers are so out of scale is because this formula is meant to track the gravity between different sized objects. This object would probably have a mass of 234 kilograms, which is a lot. That might make it a vehicle, maybe a small asteroid. An object of this mass is like a moon or a planet. And ultimately, our A term will come out to negative 1.03 times 10 to the 24th power. Technically, it would be a little bit less than that, but this mass is so huge compared to this mass that the difference between them is really inconsequential, especially when we factor specifically to the hundredth place on this number. The main thing here is negative 1.03 times 10 to the 24th. Next, B. B equals 2R M1, it's going to be 2 times our R is 3.84, yes, times 10 to the 9th, and our M1 is 324. That's going to give us a grand total for B of 2.488, I'm going to round that to the hundredths place, times 10 to the 12th. That is our B. Got some very large numbers at play here because, again, this formula would be used for solar system scale gravitational forces. Lastly, C R squared times M1, so 3.84 times 10 to the 9th. That number is then squared, then multiplied by 324. So in one's calculator, I would advise typing in open parentheses 3.84 E9. That's the times 10 to the power of E, not the natural log E. So I've got this number in its own set of parentheses I'm then going to just square that one number. Do that by itself. Hit the square button, so it's just this big number squared. Press enter. Then I'm going to multiply it separate on a separate line by 324. And do please confirm that you can get to this same number using your own work. That gave me a total of 4.78 times 10 to the 21st. So, we have our A, B, and C. They're giant monsters, though we have them. Now that we have them, we can use our quadratic. Just going to put them in, work it out, one piece at a time. I'm now officially out of board, at least out of front board. So I'm going to put the next line on the sideboard, just to get you guys started on it. So D equals, big number time, negative b, so negative 2.49 times, I'm just going to start writing out E12 plus or minus square root of b squared, so 2.49 E12 squared minus 4 times a, negative 103 E24 times b, 4.78 E21. All that over 2 times a, which is negative 1.3 E24. We in the physics industry would refer to this as a doozy. Again, in the original formula, we are looking at gravitational forces between planets and moons. And the D in that formula represents how far apart these things are. And most objects in our solar system tend to be very, very, very far apart. So odds are this formula is going to give us some very large numbers. Positive or negative, they're going to be large, because we're talking about the distance scale of planets and stars. Okay?
You can look at my calculator and make sure I'm not.
Thank you. Yes. The error of the quadratic would most commonly give us would be an imaginary, but I don't think there should be one here. Okay, good. usually what I like to do is try to simplify things by another line before I put it all onto the calculator at once. So let me do that with you guys. E12 squared. And then -4 times -1.03 E24 times 4 E21 will be positive 1.6967 E46. The numbers just keep getting bigger. And then 2 times -103, -1.03 E24. So the denominator is -2.06 E24. Thankfully, the combination of -4 times -a means that everything in the square root should be a positive number. So I would hope and expect that there wouldn't be an imaginary error message on your calculator. So do please have things reduced down to this step. All that comes left is just the remaining simplifying and finishing things off. You will get 2 values for D, and if one is positive and one is negative, that is perfectly okay. In this type of formula, the negative just tells you the direction of the distance. Yes?
So usually for quadratics, like I can just plug what's underneath the radical in, and then it's still under the radical, but I can get one thing together. And I do that, but when I do it, I got a different number. My number's smaller than your second number, and you haven't even combined that. So,
Has it taken the square root already?
yeah, I just plugged in, so the first portion on that board, I just plugged in the big 2 squared minus 4 and the A and C, and it gave me 1.9696 times 10 to the 46, but that's similar to your second number. So do I need to do the squared portion first and then subtract it by the other half? I don't know why the calculator would be messing up on it. Or maybe
Yes.
I'll figure it out.
I would square this first to get to this number, combine these to get this number, then add them together. That said, this number is just squintillion times larger than this one. So
So
when you
that's
add them
the
together,
four.
you're really just going to get this number again.
Because that's the first part is the squared plus the 4 AC part.
Correct.
Right?
And when you get numbers this big, really only the biggest number has any power. Have this copied, and as you are backing up to go, I want to, on the board, show how to take what we found here and use it for 21. Again, the formulas began the same way, but instead of canceling G and M2, we can cancel K and Q2. And all the math to get to this point for 21 would be the same. The only difference is what constants are present. So for 21, it would look like Q1 minus Q3 times d squared plus 2r Q1 times d plus r squared Q1 equals 0. Really just replacing m's with q's. You can use the same things, just plug the new numbers for q in instead of r m's. And just to help circle things, that's our C, that's our B, and that is our A. That's the period for this week. Please be working on this over the weekend. Work on them together, by all means, please. Because if you're working on them together, you'll help troubleshoot each other's problems. And when you come back Wednesday, we'll have time to answer questions, finish things out together before I accept it. I will probably be putting the next assignment on Brightspace so that if you finish and want to look at it, you can, but you don't have to. We'll have all next week to work on them together. Send me your questions by email. Please do it. If you have problems, I want to help you. I want to help you fix it before you get your stuff. Thank you all. Please have a wonderful weekend.
Figure out
Ah, nuts. I got so sidetracked.